not only in chemistry, but in science. It's called Le Chatelier's principle, and it is a principle that we didn't create, we didn't invent, we observed by watching Mother Nature. Okay? For example, Ryan, believe it or not, is used by Mother Nature in order to make Le Chatelier's principle come to life. For example, in nature, if we have too much food and not enough predator, what happens to the amount of deer? Okay. All right. It goes back up. It goes up. And what happens if hunters such as yourself do not cull the herd? And then they use up all their food, and then how does Mother Nature deal with them? They die of slow, painful death of starvation. Okay? Mother Nature uses carnivores, or in the case of Ryan, uses hunters in order to keep that population down. To us who love Bambi and we love deer and they're so pretty, we feel like they are terrible, horrible people, terrible, horrible animals. Okay, but the fact is that without them, Bambi would, and Bambi's family, entire family, including, what was the name of the girl? No, the girl that he, Fawn, was it Fawn? Okay, his entire family would die a slow, painful death of starvation if there's not enough food. Okay, so it's called Le Chatelier's principle. Mother Nature tends to want there to be a balance. Okay? And if something happens to get the thing out of balance, then Mother Nature will make it go in one direction or another in order to reestablish the balance. An hour ago, I was kind of hungry, and I realized I had a bag of M&Ms. This is basically chocolate-flavored sugar. Okay? So I inserted this sugar into my bloodstream, got my sugar levels out of whack. Okay? How did Mother Nature in my bloodstream deal with things being out of whack? Does anyone know what happens? That's right. The pancreas produces insulin, which is a gatekeeper. And insulin will open the door to allow the sugar to go into the cells. Without insulin, we would die. Because even the process of eating gets our system out of whack, out of balance. Le Chatelier's principle basically says that whenever you have a system in balance and it gets out of balance, it will move in one direction or another in order to get back in balance.
Life is all about balance. You want to have a balanced bank account, balanced diet, balance between work and play, and a healthy inner ear to keep you from falling down all the time. And lots of things can mess up that balance. One bad night at the Cheesecake Factory and you might wake up with your finances, social life, and health out of whack. In science, our word for balance is equilibrium. You've heard of it. When the balance of some natural system gets disrupted, we say that it's out of equilibrium. But that's not always a bad thing, because nature usually finds a way to restore the balance. Like if a population of deer in a forest suddenly goes nuts and there's too many of them, they'll run out of food and space and predators will move in and the population will usually fall back to where the habitat can sustain it. Likewise, there's no reason that I can't enjoy the occasional Hot Pocket without destroying my so-called balanced diet. I just have to be sure to eat something that wasn't prepared in the salty lard factory to balance it out. We tend to think of chemical reactions as having a beginning and an end. You start with some reactants, some chemistry happens, and you end up with the products, and that's that. But that's not that, because you don't usually end up with pure products. Many chemical reactions seek balance too, and just like us, they have to work through the stress in order to find.
All right. So, notice that in the previous examples, I always gave you a temperature, and actually some of you actually pointed it out to me and asked me, what am I supposed to do with this temperature? Well, at that point, nothing. But hopefully after today's lecture you'll realize that that temperature is important because the K value is specific to that temperature. Change temperature, change the K value. So if a system is in equilibrium and you change the concentrations of the reactants or products, or you change the temperature, or you change the pressure, it will react by going in one direction or another in order to undo the damage. Le Chatelier's principle states, if a change is imposed on a system at equilibrium, the position of the equilibrium will shift in order to reduce the change. If a change is imposed on a system in equilibrium, the position of the equilibrium will shift in a direction that tends to reduce the change.
But sometimes there is, if you will, a disturbance in the Force, and as any good Jedi knows, those things must be put right. Chemical equilibria can be disturbed by changes in the concentration of one or more substances, or by changes in temperature or pressure. We describe these changes based on which way they force the equilibrium. We say a change shifts the reaction to the right if it tends to make more products form, and to the left if it tends to make more reactants form. This was all summarized nicely by a French chemist named Henri-Louis Le Chatelier, who was born in Paris in 1850. Today, we call his summary Le Chatelier's principle, and it says that if stress is placed on a system that is at equilibrium, the system will proceed in a direction that minimizes the stress. That can happen in several ways. For starters, changing the concentration of any substance in a reaction causes it to proceed in whatever direction restores the former balance. For example, once the Haber reaction is at equilibrium, if you were to add more nitrogen gas to the mix, the existing hydrogen would have more nitrogen to react with. Thus, it would begin forming more ammonia, sending the reaction noticeably to the right until the reaction balances itself again. Removing some of the ammonia would have the same effect. There would be less ammonia available to break down, so the formation of ammonia would temporarily exceed the formation of nitrogen and hydrogen, and the reaction would again shift to the right until the balance is restored. Now here's an ironic side of irony served up for you. In 1901, Le Chatelier tried to invent a process for fixing nitrogen, to make ammonia from nitrogen and hydrogen. But he gave up the effort after the experiment caused a huge explosion that killed one of his lab assistants. 8 years later, the German chemist Fritz Haber, probably the closest the world ever got to a literal evil genius, did just what Le Chatelier was trying to do.
Fritz Haber was probably trying to make weapons. Okay? Now, this is before Nazism. His process led to the death of thousands, maybe hundreds of thousands of people. But his process has also led to the life of millions upon millions upon millions of people. His process has led to us being able to mass produce fertilizer, which has allowed us to also increase our crops and feed the world. So was he an evil genius or a wonderful, beneficent, nice guy? I don't know. What? Okay, there are three possibilities. Change the concentrations. He created the process. You see, when you make ammonia, at a certain point it reaches equilibrium and it stops making ammonia. He was able to figure out a way in which you could keep making ammonia and it never actually reach equilibrium. You understand? Okay, so let me explain this to you. All right, so you have here, be careful with this reaction. A solid plus a solid forms a gas and 6 CO gases. Okay? So, what happens if you add carbon monoxide? The best thing to do is, in your mind's eye, take your hands like this, and your right hand is where you keep your reactants, and your left hand is where you keep your products. Okay? So we're adding carbon monoxide. Carbon monoxide is a product. So what happens? Uh-oh. This is too heavy. We're adding carbon monoxide, which is making me shift the K value in this direction. I am out of balance. How can I go in this direction now? Well, we can't add reactants, but we can make the reaction. See, let's go back here. It was in perfect balance here. Reactant, product, reactant, product. Then somebody came around and added product. Got things out of balance. So in which direction can the reaction go in order to get things back in balance? Reactants, reactants, reactants. And now we're back in balance. We're back to where our K value originally was. Okay? So the answer to the question is, it will go to the left. That's it. Will the K value change? Did I get back into the original spot? Yes. The K value does not change. The K value does not change. Okay, so what happens if you add or remove carbon or AS406? Reactant products, reactant products. What happens? The reactants is heavier? I disagree with you, respectfully. Look, the products are heavier, considering you're adding or removing reactants.
Oh, no, my bad, my bad.
What is it?
Yeah, no, you were right. You're right.
No, I didn't say anything.
No,
I was agreeing with him.
Wrong thing.
Okay, guys.
You have more products.
Guys, look at the reactants. What's the phase of the reactants?
Solids.
Solids. Do solids play a... Are solids going to be in any one of these? No. So what happens if you add or remove solids? Nothing happens. Nothing happens. So the answer to this is a big fat nothing. Nothing happens. Because you're adding or removing solids. Okay, let's get back in balance. This time we are removing what? Reactant or a product? And is that product a gas or aqueous? Uh-oh. This is too light, making this side too heavy. Uh-oh. Uh-oh. Okay, what happens to the K value? The K value goes down. So what needs to happen?
You need to add reactants.
Make reactants. Make reactants. Make products, make products, make products until I'm back in balance again. So the answer is go to the right. What happens when the K value, what happens to the K value when you go to the right? Where did I go back to?
It goes up.
No, I went up because I had gone down. Let's go again. Reactant product, reactant product. So I have, somebody took away my product. So my K value went down. So how did I adjust? Make more products, make more products, make more products. Now I'm back to the same spot. So what happened to the K value? No change. All right, so K value is not going to be changed by a change in the reactants or products. All right, you need to cut that temperature. But you need to treat energy like if it was a reactant or a product. If the reaction is exothermic, you're producing energy, so it's like a product. If the reaction is endothermic, you are absorbing energy, so it's like a reactant. They're going to tell you whether a reaction is exothermic or endothermic by telling you the delta H. Delta H is the change in heat. This is perhaps the most important thing to remember. If delta H is negative, it's exothermic. If delta H is positive, it's endothermic. If delta H is negative, it's exothermic. If delta H is positive, it's endothermic. When you shift toward the product side, is energy absorbed or released? Look at the delta H. Positive or negative? Positive. So it's absorb energy, release energy. Absorb, release. Absorb, release. So I'm constantly flipping back and forth. Absorb, release. Absorb, release. All right, so I'm happy, I'm in equilibrium, I'm in balance. What happens if you increase the temperature in the room? It's hot. Okay, it's too hot. I am too hot. So in which direction will the reaction go in order to deal with this room being too hot? Let's review. Absorb energy, release energy. Absorb energy. What do you do to the room if you're absorbing its energy? What do you do to the room if you're releasing its energy? Okay, now think. In which direction will it go? Absorb, release. Absorb, release. If the room gets too hot. Absorb, absorb. The room is cooling down. This is it. Absorb. The room has cooled down again. Absorb, release. Absorb, release. What happened to my K value? Okay, is this getting bigger or smaller? Think about it. K is products over reactants. I've made more products, so the K value is bigger. Okay, so an increase in temperature for an endothermic reaction will result in it going to the right, and the K value goes up. Unlike when we change the concentration, in which case the K value went down. All right. I'm sorry, in which case the K value stayed the same. Let's do another example. We're in balance here. Reactants, products. What kind of reaction is this? Exo or endo?
Exo.
How do you know?
Increase.
No.
Negative delta.
It's a negative delta H, which means it's exo. So that means release energy, absorb energy. Release energy, absorb energy. What happens if the room gets too hot? Release, absorb. Release, absorb. Which direction do you go? Absorb. Absorb. The room is cooling down. The room is cooling down. So I created more reactants. Unfortunately, I messed up my K value. My K is now smaller or bigger.
But changing concentrations is only one part, or actually only 1/3 of the story. There's also pressure to consider. If you look at the equation for the Haber process, for example, you can see that 4 moles of gas react to form 2 moles of gas. So the forward reaction decreases the volume, while the reverse reaction increases it. This is important. Increasing the pressure will then put more stress on the high-volume reactants than the low-volume products, so the reaction shifts to the right.
Okay, has anyone here ever had to move into a smaller house? Okay, you know what that feels like. Whereas you had this much room in your bedroom, now you have less room. So what are some of the things, practical things that you did in order to deal with that, Phoebe? Okay, to share space, you shared a room with your sister. What did you do with your stuff in order to... Some of you got rid. Did you buy any... Did your mom go to Bed Bath & Beyond and find some fun ways, some interesting ways in order to create more space? Yeah. There are lots of space savers. You can actually... What we do is we lift up our beds, and instead of having just dust under our beds, we lift up our beds, giving us enough room to put crates and boxes under our bed, and then we have a bed skirt so no one can see we've got a bunch of stuff underneath. Now, if we were to move into our larger house, forget that. We're getting all that stuff that we're hiding under the bed and we're putting it in our large closet. We have a teeny tiny little closet. We don't have that space. Okay, that's basically what's going on here. This is how systems in equilibrium will react when you increase the pressure. When you're increasing the pressure, what are you doing to the size of the house? Smaller. So you're going to have to be more compact. You're going to have to be smarter about the way you store things. Okay? What happens if you decrease the pressure? It gets bigger, so are you needing to be as careful with how you store things? No, you don't. Okay, so what you want to do here is notice that this was the Haber reaction where you had hydrogens and nitrogens on one side and then ammonia that combines the two on the other side. What happened? In which direction did it go? Did it go toward the ammonia side or did it go toward the individual gas side when you increased the pressure? Did you notice how all the gases became ammonia? Why? It was more compact. It took up less space in that direction. Another way of looking at it is there are some airliners now that are getting really, really sticky about the number of suitcases. Back when I was a kid, you could have 3, 4, 5, however many suitcases you wanted, you could have. Okay? Now, these days, my goodness gracious. Some airlines charge you for one suitcase. Some give you just one, right? And your carry-on. Some will start charging after 2. So, if you are having to go from an airline that allows all the suitcases you want to an airline that requires only one, what are you going to have to do halfway through your trip? You're going to have to take everything out of your 4 suitcases into one. All right? You're shifting into the more compact way of doing things. If you're used to using only one and they allow you to use 2 or 3, then by all means, spread out. Okay?
Producing more ammonia than it does at low pressure. And indeed, the industrial Haber process is done at 200 atmospheres of pressure. Decreasing the pressure, meanwhile, has the opposite effect.
Okay, notice it's all ammonia here, but what happens when you give
The reaction proceeds in the direction that raises the pressure back to where it was
see
before.
that?
In this case, that's the breakdown of ammonia toward the left, where there are...
Yes?
But how would they utilize the ammonia if the minute they release the pressure it starts to decompose?
They will extract it usually by condensing it. And at that point, it's no longer in equilibrium. Yes? Okay. Okay, so how many suitcases do you have on the reactant side? 4, right? 1 and 3 is 4. How many suitcases do you have on the product side? 2. So if you increase the pressure and therefore reduce the size, it goes toward the product side. If you decrease the pressure and increase the size, it goes to the left.
4 moles of gas. Solids and liquids aren't affected by pressure as much, so the more gases that are present in a reaction, the greater effect that any pressure change will have. The third...
All right. So, here we go. In order to get these, whenever you're dealing with pressure, all you need to do is count the number of suitcases on either side. You ready? Yeah. How many suitcases on this side? No, because solids and liquids don't count. They're carry-ons. 6. And how many on this side? 4. So what happens if you reduce the volume? Which direction will it go? It goes to the right. I'm sorry. How many suitcases do you have on this side? 0, because that's a liquid. So, if you reduce the size, it's a liquid. Solids and liquids don't count. Think of them as carry-ons. Understand? So, if you have to go to a smaller size, you're going to need to go to the right so that you're more compact, you have less suitcases to worry about. Okay? But what happens to your K value if you go to the right and you produce more products? Increase or decrease? An increase. Because remember that K is products over... So if this goes up and this goes down, your number goes up. All right, let's see if I can get this one right. How many suitcases on the left? How many suitcases on the right? So what happens if you reduce the size? Which direction does it go? Goes to the right again. K value. How about this one? How many gases? How many gases? So what happens if you reduce the size? Nothing happens. Why? Same number of suitcases. Same number of suitcases. All right, this will summarize it all in a way that Marie will appreciate. Ever been to Surrey? Somewhere in here.
Systems in dynamic equilibrium are very sensitive to changes in concentration, pressure, and temperature. Le Chatelier's principle enables us to predict the effect of these changes. It states that if a system in dynamic equilibrium is disturbed, the equilibrium position shifts to counteract the disturbance. For example, if more reactants are added, the system removes them by creating more products. If products are removed, the system replaces them by converting reactants. Consider the Haber process, in which nitrogen and hydrogen react to form ammonia. Le Chatelier's principle tells us that if the pressure on the system increases, the equilibrium position shifts to the side where there are fewer moles of gas, and hence a lower pressure. The forward reaction is exothermic. Energy is released when ammonia is formed. Increasing the temperature drives the equilibrium position to the endothermic left-hand side, as the system absorbs additional heat energy from the surroundings. Decreasing the temperature drives the equilibrium position towards the exothermic right-hand side. The system gives heat energy back to the surroundings. A better yield is obtained at lower temperatures, but this benefit is offset by a slower reaction. Industrially, a temperature of 450 degrees Celsius, a pressure of 200 atmospheres, and an iron catalyst is used.